us begin with the introduction. Logic is one of the fundamental topics in discrete mathematics. It focuses on how we use information and reasoning to reach valid conclusions. The basic element of logic is a proposition, which is a statement that can only be either true or false. From these simple propositions, we can create more complex statements using logical connectives. In MAT210, we study concepts such as conditional statements, biconditional statements, truth tables, and rules of inference. These concepts can help us to determine whether an argument is logically valid. Although logic may seem theoretical, it is widely used in everyday life. For example, when a university states that a student may sit for an examination only if their attendance exceeds 80%, it is using a conditional statement. Similarly, when an online store offers free shipping, if and only if a customer is a premium member, it is applying a biconditional statement. In addition, whenever we combine known facts to make a decision or reach a conclusion, we are applying rules of inference. The purpose of this report is to explain three important areas of logic: condition and biconditional statements, truth tables, and arguments with the rules of inference. Through explanations and example, we aim to show that logic is not just a mathematical concept, but also a practical tool for reasoning and problem solving in real-life situations. A conditional statement, written as P implies Q or P arrow Q, is a logical statement that shows a relationship between two propositions. It means that if a proposition P is true, then proposition Q must also be true. However, if P is true and Q is false, then the statement becomes false. In all other cases, the conditional statement is considered true. Next, a biconditional statement, written as P if and only if Q, or PQ, is a logical statement where both propositions depends on each other. It means P is true if Q is true, and Q is true if P is true. A biconditional statement is true only when both propositions have the same true value, either both true or both false. If their true value are different, then the statement is false.
Before we applying logic to real situations, it is important to understand what an argument is and how rules of inference work. In logic, an argument is a sequence of premises that lead to a conclusion. An argument is considered valid if the conclusion must be true whenever all the premises are true. To move from premises to a conclusion, we use rules of inference. These are accepted logical patterns that preserve validity and helps us reason correctly. Some common rules include modus ponens, modus tollens, hypothetical syllogism, and disjunctive syllogism. Each rule provides a structured way to derive the new information from statements that are already known to be true. The key idea is that validity depends on the logical structure of the arguments, not on whether the individual statements are actually true in real life. The process is simple. Start with the given premise, apply the appropriate rule step by step, and continue until a conclusion is reached. If the conclusion follow necessarily from the premises, then the argument is valid. Overall, rules of inference are important because they help us construct logical proofs, solve problems systematically, and make reliable decisions based on sound reasoning.
Next, I will explain the application of conditional and biconditional statements in real life. First, we define two propositions. Let P represents the student has completed all required credit hours, and Q represents the student is eligible to graduate. From these propositions, we found the conditional statement P implies Q, which means if a student completes all required credit hours, then the student is eligible to graduate. To determine whether this statement is true or false, we use a truth table. As shown, A conditional statement is only false when P is true and Q is false. In all other cases, the statement is true. We can also create three related forms of the statement: the converse, inverse, and contrapositive. These forms help us analyze the validity and logical relationship of the original statement. The key takeaway is that conditional statements provide a structured way to reason and make decisions. They are widely used in university regulations, system access rules, online services, and many everyday situations based on if-then concept. This example shows how logic helps us understand and evaluate real-life conditions clearly and systematically. Now, I will explain the role of truth tables in logic. A truth table is a tool used to determine whether two statements are logically equivalent. In this example, we compare two statements based on De Morgan's law. Let P represent the student attends the lecture and Q represent the student submits the assignment. The two statements being compared are not P and Q written as negation P intercept Q and not P or not Q written as negation P union negation Q. To test whether these statements have the same meaning, we list all possible true values of P and Q in the truth table and calculate the results for both expressions. As shown in the final two columns, the truth values are identical in every row. Since the result match for all possible cases, the two statements are logically equivalent. This demonstrates the Morgan's law and shows how truth tables help us verify logical relationships. In real life, truth tables are useful for decision making, rule checking, and ensuring that different statements actually convey the same meaning. The key takeaway is that different wording can sometimes express exactly the same logical idea.
Next, let's look at an example on how arguments and rules of inference are implied in real academic situation. In this example, a student is planning their next semester's courses based on university's course unique requirements. We are given three premises. The first premise states that if a student passes calculus 1, then they may enroll in calculus 2. The second premise states that if a student may enroll in calculus 2, then they may enroll in linear algebra. The third premise tells us that the student has already passes calculus 1. To analyze this logically, we represent the statements using propositions. Let P represent the student passes calculus 1, let Q represent the student may enroll in calculus 2, and let R represent the student may enroll in linear algebra. The premises can then be written as P implies Q, Q implies R, and P. Next, we apply the rules of inference. Using hypothetical syllogism, we combine the first two premises and obtain P implies R. This means that if the student passes calculus 1, then the student may enroll in linear algebra. Since premise 3 confirms that P is true, we apply modus ponens and conclude that R is also true. Therefore, the final conclusion is that the student may enroll in linear algebra. This example demonstrates how logical arguments and inference rules can be used to reach a valid conclusion in a clear and systematic way.
To conclude, this report explored three important areas of propositional logic in MAT210: conditional and biconditional statements, truth tables, and arguments with rules of inference. First, we examine conditional and biconditional statements through a graduation policy example. We learn how a statement can be transformed into its converse, inverse, and contrapositive, and that only the original statement and its contrapositive are always logically equivalent. Next, we use truth tables to compare logical statements. By checking every possible combination of true values, we verify logical equivalence and demonstrated De Morgan's law. Finally, we apply rules of inference such as hypothetical syllogism and modus ponens to drive valid conclusions from a set of premises. This showed how logic helped us move systematically from facts to conclusions. Overall, logic is much more than a theoretical concept. It is a practical tool that helps us organize reasoning, evaluate information, test rules, and make sound decisions in real life situations. Thank you for your attention.